All right, so I want to talk a little bit about section 7.2, which talks about how to do a chi-squared goodness of fit test for an association between two categorical variables. So, and I want to make a connection between what we're talking about in 7.2 and what we talked about in P.1, which is two random events being independent. And what does that have to do with no association between categorical variables? So from section P.1, just a quick review of that here, is we say two events are independent if they don't affect each other. So in other words, the probability of event A happening, if B already happened, is equal to the overall probability of A happening. So we write that this way. The probability of A if B, that's written out that way. And then the probability of just A is written that way. So if those two are equal, that means that the two events are independent. Now remember, independent doesn't mean the same thing as they can't happen together. So if you have A over here and B over here, that is not independent. That means either disjoint or mutually exclusive. That's a common mistake, to get mutually exclusive and independent mixed up. So that's not what we're talking about here. So let's look at an example of things that are independent. So let's say you roll a die and flip a coin. Event A is going to be the coin is heads, and event B is that the die is a result of 5. Now these events are independent because we know that the result of the coin is not going to affect the result of the die and vice versa. So that's what it means for them to be independent. And so this is going to be true. So with that in mind, let's do some math here. Let's fill in what this means with the actual numbers. So first of all, if you want to get just the probability of A, the probability of A means the probability that the coin will be heads. And if it is a fair coin and you flip it, half of the time it's going to be heads. So that's 0.5 or 50%. So that's the overall probability of heads here. Now, the overall probability of not heads, of getting tails, is what's going to go over here. That's also going to be 0.5. Now, the overall probability of anything happening is always going to be 1, or 100%. Now, the probability of B, that's what's going to go in here. The overall probability of B is going to be the probability of getting a 5 when you roll a die. That should be a 1 out of 6 chance, because there's 6 faces on the die and they're all equally likely. So this is going to be 1 out of 6, which comes out to be about 0.1667, with the 6s going on forever if you don't round it off. So about 16.7% of the time. And the probability of not B is the rest of the time. That's going to be 1 minus the probability of B, or 1 minus 0.1667, which comes out to be 0.8333. Okay, so Now, how do we get the probability of A and B? This is what I want to sort of focus on here. The probability of A and B, well, let's think. I know, like, out of the times that you get a 5 on the die, half of that time you should be getting a heads here. So let's remember some rules here. I'm going to make some room here. So the formula for the probability of A if B is the probability of A and B happening divided by the probability of B. So out of all the times that B happens, what proportion of the time does A also happen? And because these are independent, I know that the probability of A if B is going to be the same as the probability of A, right? Which is equal to 0.5. And that should be the same as this. So, and that thing is 0.5. So you could write this as 0.5 here. Or actually, let's do it without numbers now. So what we're trying to find is the probability of A and B. That's this thing. And to get that, you could multiply both sides of this equation by the probability of B. So to cancel out that division. So that will give you the probability of A times the probability of B equals the thing we want, the probability of A and B. So now we know the probability of A and we know the probability of B. There's the 0.5, which you can write as 1/2, and then the 0.1667, which you can write as 1/6, equals what we're trying to find. So if events are independent, this is a way you can find the probability of both of them happening. And you could also just multiply the decimals. You could do 0.5 times 0.1667, and you'll get 0.0833, I believe. Yep. Okay, so likewise, you could do the same thing to find the probability of getting tails and getting a 5. That's also going to be this probability, the 0.5 times the probability of B. So that's going to be the same thing. It's still going to be 0.08333. Now, if you want to know the probability of not B, that's the 0.8333, and getting A and not B. So likewise, to get this one, the combination of these two events is equal to the probability of not B times the probability of A. So we're just going to multiply those together using the fact that they are independent. So that's going to be 0.5 times 5/6 is 0.4167. And this is going to be the same thing. Okay, now let's look at a related question. Let's say you repeat this experiment 1,200 times. So you roll the die, flip the coin, write down what happens, and then do that 1,199 more times. So let's look at what might happen here. Now, we're going to make a weird assumption here that everything happens perfectly, that there's no randomness. Well, I guess there is randomness, but you just end up with exactly 600 heads and 600 tails, which is very unlikely to happen in the real world. Like, you're more likely to get like 590 and 610 or all kinds of other things, but somewhere around 600. So if everything, we're just going to assume things work out perfectly here to make the math a little easier, to try to, I want to explain one of the formulas that they use in 7.2 a little bit more to make a connection between 7.2 and p.1. So, and this will be easier if we just assume that everything works out perfectly. So what will happen with the the die results, I mean. So the die gets rolled 1,200 times. 1/6 out of those 1,200 die rolls should end up being a 5. So that will come out to be 200. And the other 5/6 of the time is when you don't get a 5. Okay, so that's that. Now, if there's no association between these two categorical variables, so the categorical variables are the result of the coin flip, and the other categorical variable is the result of the die roll. Now, because there's no association here, or in other words, they are independent, we can use this formula. We know what the probability of this is going to be. The probability, we know the probability of A and B is going to be 1/2 times 1/6, just like we calculated that before, which comes out to be 1/12 or 0.0833 approximately. Now, how does that tell you the count that should be here? So this is going to be the expected, if everything works out perfectly, it's going to be that fraction of the total, 1/12 out of the 1,200, which comes out to 100. I also want to notice that the way you can get that, another way of calculating this is, what if we write it as half of 200? That's also going to come out to be 100. And it should be half of 200 because that's the total number of times you get a 5. So half of that time, you should get also a heads. Now you could write it as half of 200. You could also write it as 1/6 of the number of heads that you got. Because out of the times that you had heads, 1/6 of that time, you should get a 5. So these are all different ways of calculating the same thing. These all come out to be 100. What if we thought about it, well, not thinking about it a different way, but what I want to show is that all of these calculations, we could think of it as doing 200 out of, well, sorry, let's see. Instead of the 1/2, I want to write this 1/2 as 600 out of 1,200. That's the proportion of the time that you get heads there. So that's 600 out of 1,200 times 200. And instead of 1/6, what if you write that as 200 over 1,200? That's the same thing. either way, you could, both of these things, when you multiply them, you're going to multiply the 200 over 1, where you multiply the tops of the fractions and the bottoms together. And same thing over here. When you multiply the tops and the bottoms, you're going to get 200 times 600 over 1200. And this is the formula that they cover in the book. What I'm trying to say is that that's the same thing as if you do the probability of A and B, and you multiply that by the total count. So, likewise, we can do this with the rest of them. We could take the probability of not A, meaning you get tails, multiplied by the probability of getting a 5, and this should also be 100. And if you want to calculate this one, you could do it either way. You could use this formula here, where we're going to take the count of heads times the overall count of not B, which means not a 5, which is going to be 600 times 1,000, and divide that by the total, 1,200. That's going to end up being the same thing as if you do, well, let's see, what is the probability of this thing happening? It was 0.4167. And 0.4167 is also known as 5/12. So if you do 5/12 times the total, it should come out to the same thing. So that's going to be $500. Whether you do it that way, or if you do 600 times 1,000 divided by 1,200, you still get 500. And this is also going to be 500. So that's what might happen if everything works out perfectly and you get exactly half of your coin flips are going to be heads. But, you know, in real life, that's not very likely to happen. Something that's more likely to happen is you might get 585 heads and 615 tails, and instead of getting 200 of these, you might get 212, and then 988, and given that, you could still find the expected thing that would go in here. You could still do 212 times 585. Divided by the 1,200, and yeah, you're gonna get about 103 or something. But because there's random variation, who knows? You might get 97. And everything else is gonna have to be some more or less random numbers that are sort of proportional, but not exactly. So something like that is the kind of thing that happens regularly. You're probably not going to get exactly half of the time heads. Now, let's talk about a quick example of things that are not independent. So, let's say you ask 300 people their gender, and if their hair is longer than 6 inches or not. And so you end up with 160 men in your random sample and 140 women in your random sample, and that has to add up to 300, of course. And as is likely to happen, you're going to get more short-haired men and more long-haired women. So this is an example of where things are not independent. So if these were independent, then the probability of out of one of these random people getting a long-haired man, the probability of being male and long-haired, would be the probability of m times the probability of L. And so the probability of m here is, let's see, 160 out of 300 is a probability of getting a random man, a little bit more than 50% because it's random, times the probability of a long-haired person, which is 121 out of 300. Maybe I shouldn't have highlighted this because it's not exactly, this is the probability, which isn't the same thing as the count. So the count of long-haired men would be the probability of getting a long-haired man multiplied by the total number of everybody. So it would be whatever this result comes out to be times 300. So that would be 160 divided by 300 times 121 divided by 300. That is all getting multiplied by the total number that you have there. And you can see that the 300s would cancel out, and you end up with 160 times 121 divided by 300, which is the formula that they show you in the 7.2 interactive lecture video. So we can calculate that here. We want to do 160 times 121 divided by 300. Comes out to be about 64.53. That's how I got that. And that's what there would be if there's no association. That's how many long-haired men there would be if we were just given the numbers on the outside and we're trying to find the counts on the inside. So, anyways, that's how one way we can tell that these events are not independent. So you could say the events M and L are not independent because we had a very big difference between the expected count of long-haired men if they were independent compared to what we actually got. And what 7.2 goes on to figure out is how to use a chi-square test to see how unlikely this would be, like how to get a p-value that represents how unlikely getting 18, which is way lower than 64, would be if they were actually independent. So anyways, these events are not independent. What I'm sort of also trying to go over here is that means the same thing as saying there is an association or a correlation between the variables gender and hair length. So that's what I wanted to go over here. Most of this is going to be explained in the 7.2 video, but the 7.2 video doesn't really make a connection between p.1, and I think it's important to make connections between different things you're learning as you go. So talk to you later.